the logarithmic functions. Previous section, we talked about the exponential functions and the natural exponential function. In this case, we will talk about logarithmic functions, which are in effect inverses of each other. So exponential functions and logarithmic functions are inverses of each other. Okay, so before we dig deep into this section, please remember that to read through the textbook section before we cover it in class, or you watch this video, just spend half an hour to 45 minutes, peruse through the textbook section 4.3 before you watch this video or come to class. Then attend the class and take lecture notes, or watch this video and take notes on any questions you might have, or on any points of the lecture that you think are particularly important. And then review your lecture notes and solve all the examples that you saw in this video or in the book on your own without looking at the solutions. And then complete all the homework assignments and review. And of course, it goes without saying that through this process, any questions you have, you should come and ask me about it. Okay? So, the logarithmic functions, this first sentence is so important. If you remember this first sentence, it'll significantly simplify solving all logarithmic expressions. So, the logarithmic function generates an exponent. This is critical to remember. Okay, it is the only function in mathematics that does that. So what does that mean? So that means in this logarithmic equation, the y is a generated exponent. So y is always an exponent to something, to some base. The question is, to what base? Well, take a look at the base of the log function. It is y. Y is the exponent to that base, which will then equal to this result, x. So let's look at that breakdown here in this list. Y is an exponent because log functions generate an exponent. A is the base of that exponent. That A is the base of that exponent because every exponent should have a base, right? So A, or the base of the log function, becomes the base of the exponent. And x is the result of this base raised to that exponent y. Once again, x is the result of raising this base to that exponent. Okay, you can see that clearly here. So we said that logarithmic functions generate an exponent. So y must be an exponent right there. Y is an exponent to base a equals this result, x. Okay, so it's listed here, but maybe it's clear if I also show it diagrammatically here. So that is the result. The y, or the a, sorry, the a is the base, and the y is the exponent. Okay? So, if a digit, if the digit a is missing, then the base of the logarithmic function must be 10. If a digit a is missing, the base is missing, or if it's not written, missing means it wasn't written, then the base of the logarithmic function must be 10. That's by mathematical convention. So these two are identical expressions. So if you don't write the 10, if you write the 10, it's not an error. It's just that usually you don't see it written when, in fact, the base of a log function is equal to 10. Okay, so the log of a negative, these are other things we should know before we look into some examples. The log of a negative number does not exist. Try it on your calculator. Let's do that. So if I take the log of, let's say, -1, right? Pick an easy number. So here we have the log of -1, enter, error, right? It does not exist. Let's say -5, error again. Okay? So the log of a negative number does not exist. On the other hand, the log of a number between 0 and 1 is a negative number. And it says try it on your calculator. Let's do that. So the log of any number between 0 and 1 is a negative number. So let's take the log of 0.325. So we would expect that to be a negative number. And there it is. Okay, -0.488. So the log of a negative number does not exist, but the log of any number between 0 and 1 is a negative number. Okay. So the natural logarithmic function is any log function to base e, which we already talked about in the previous section. Log to base e of x is equal to the ln x, or the natural log of x. Okay, this is so important, such an important function. The log to base e is such an important function that it has its own button on the calculator. Okay, as we talked about in the last section. So we have natural log, ln, right? And right above it is that blue e to the x function, or the natural exponential function, which we used in the previous video. Okay. So if you wonder what is natural ln x or natural log of x, it's the same as log, but the base is e. The base of a log function that is equal to e is equal to a natural log function. Okay, the same relationship that we talked about with respect to the log function, which was log functions generate an exponent, right? So that y is an exponent to base a, which leads to this result. So that's what we talked about here. A, or the base, to y, which is the exponent, equals x, which is the result. That same rule applies here. So if you have natural log of x equals y, that y is an exponent to some base. What base is that? This is a natural log, so the base must be e, right? So the base of a natural log function is e. E to the y power equals x, which is what you see here. So there is a very close relationship between the log or natural log function and exponential functions. They are inverses of each other. We've talked about inverse functions, right? So they are inverses of each other. Okay, so given the following logarithmic forms, convert and write the equation using the exponential form. So this is so important to be able to go from the natural log form to exponential form, or to the log form to the exponential form and back, from the exponential form to the log form, and from the exponential form back to the natural log form. This is so important to be able to go back and forth between these two forms that I thought we should do a bunch of examples on that, just to make sure that everybody's comfortable with going from the log or natural log form to the exponential form, and back from exponential form to either log form or to natural log form. Very, very important. So I would highly encourage you, no matter how much you think you don't know this yet, pause the video, answer this question on a piece of scratch paper, and then unpause the video and look at my solutions, okay? So I'm assuming now you've done that and now you're back. Great. So the log function, as we said at the beginning of this page, generates an exponent. So this -1 is an exponent. To what base? To the base of the log function. But the log function, the base is missing. So what does that have to be then? 10. If it's missing, it must be 10. So 10 to -1, -1 power equals this result, 0.1. So we've just converted and wrote the equation in exponential form. That is the exponential form. Okay, the log is gone. Instead, you have an exponential form of that. With the power can be replaced by x, some variable. Okay, here. Then we know that log and natural log functions generate an exponent, right? So we know this 2/3 is an exponent. To what base? To base 8, which is the base of the log function. So let's write that down. Log, so base 8 to that exponent, 2/3, equals 4. Okay? Can we simplify this? Absolutely, if you want to. That's all they want us to do. So I mean, we can simplify this if you want. I mean, you can show how this works, right? I'm not going to write it here because that's all they're asking for, the exponential form. But we can simplify the left-hand side, right? We know any rational exponent is equivalent to a radical expression, right? So 8 squared, 3rd root of 8 squared is the translation of the left side to radical form, equals 4, right? And then 8 squared can be written as 2 cubed squared, right? 3rd root of 8 is 2 cubed squared, like that, equals 4, right? And then we can swap these two. The 2 and 3 can be swapped because they're a product, right? 2 times 3 is the same thing as 3 times 2. So 3rd root of 2 cubed squared equals 4. Let's swap those 2 like that. That's what I meant. Swap those. That's allowed because that's 2 times 3 is the same thing as 3 times 2. Makes no difference if you swap them. Then this power on the outside is equal to the index of this root expression, so they cancel each other out, right? So 2 squared comes out, and we know that that is equal to 4 equals 4. That is a true statement. Okay? I just wanted to show you that in case you're curious. Can we simplify this? Yes. But for this case, we just want to go this far. Okay, so then we have this case where the 0 must be what? Do you remember? The 0 must be an exponent, right? Log functions and natural log functions generate an exponent. So this 0 is an exponent. So exponent is equal to 0. The base is equal to 5. And the result is equal to 1. Right? So let's put them together in the exponential form. So this base, 5, to that exponent 0 is equal to 1, this result. And I'm going to leave it like that because that's this expression written in exponential form. Okay? All right. So let's see more examples. here it says given the following exponential forms, convert and write each equation in logarithmic form. So we want to do the opposite of what we did in the previous exercise. So we know that, let's break this up into its different components, right? What the base is 10. You don't have to go through this. I'm just showing anyone who may have difficulty with this how this is done. But you can, if you're comfortable with this, you can immediately write down the logarithmic form for this exponential form. But in case you have questions here, I hope this will clear it. So base equals 10. That exponent is equal to -4, and the result is 0.0001. Okay, so now let's convert it. So we know that any log function generates an exponent, right? So this side must be -4, this side of the equality symbol. The base is 10. We can write it if you want. I mean, by mathematical convention, we don't need to write 10 as a base of a log function, but if that helps you better understand this exercise, I'm going to put it there. 10 is the base. The log function generates an exponent. The log has a base. And the result comes right here, 0.0001. Okay? Right there. So that is a translation of this exponential form into logarithmic form. Like that. If you haven't done this already, please pause the video, complete the answer to this one, and then come back to the video again. Okay, so I'm assuming you've done that, and now you're back. So let's once again break this up into its different components. The base is 2. The exponent is -3. And the result is 1/8. Okay, so let's put it together in a logarithmic expression form. So any log generates an exponent, right? So this exponent equal to -3, like that. Generates means it produces, right? Log functions produce an exponent. So there we have it. So on this side, what is the base of the log? 2. Because that was the base of the exponential function. What is the result? 1/8. So 1/8. Okay, which is the result. All right. So next example or exercise, we have, it says, given the following equations in natural logarithmic form. We know it's natural logarithmic form because of the ln, right? ln stands for natural log in reverse order. Natural log, natural log. Okay. What is the natural log base? What is the base to a natural log? Do you remember? It is the e, right? It is e. The base of the natural log is e. So given this equations in natural log form, convert the equation to exponential form. Okay, let's do that. So this is an exponent. So this is a natural log. So the base is e. The exponent must be 5, right? Natural log and log functions generate or produce an exponent. So this number 5 is an exponent to some base. So exponent is equal to 5. And the result is equal to y, right? So let's put it together in an exponential function form. So the base is e, the exponent is 5, equals y. Okay, let me box these final answers. Here and here, or y equals e to the 5th. Okay, you can also, or I mean, this is not that crucial, but y equals e to the 5th. Okay, either that or that. Okay, so this one, I hope these are matching what you have in your solution. So this one, once again, we know that natural log or log functions generate exponents. So to what base? In this case, the base of the natural log is e. The exponent is 4. And the result is all of that. The result is x minus 1. Like that. Okay, so let's piece this together again in exponential form. So we have base e to this exponent 4 equals this result, x minus 1. Or let me put the variable on this side. So x minus 1 is equal to e to the 4. They're both the same expression or equation. Okay, like that. Okay, so that is the equivalent of that expression in exponential function form or exponential form. Okay, given the following equations in exponential form, convert and write each equation in natural logarithmic form. So we're doing in number 4, we're being asked to do the opposite of what we did in number 3. Okay, let's do that. Again, I hope you complete this on your own and then come back to the video after you have your solution ready. Okay, so here the exponent, or let me begin with base because I started with base in all of these. So the base is e. We already know that, right? It's clear from the expression. Base is equal to e. The exponent, again it's clear, is equal to x plus 1. And the result is equal to 0.5, right? So let's piece this together in logarithmic form. So we know that logarithmic, or in natural log, because of the base being e, we can use natural log, right? So we know that natural log and log functions generate an exponent. So I'm going to put x plus 1 on the other side. That's an exponent. Natural log and log functions produce or generate an exponent there on the other side. The base is already e. As soon as I write natural log, the base is e. I don't have to write it, but if you want, we can write it here. It's not incorrect, it's just not done. Okay, natural log to base e of this result, 0.5. Okay, so these two expressions that you see, the exponential form and the natural log form, are equivalent to each other. And then now this one. So once again, the base here is e. The exponent is minus 40. And the result is x. Like that. Okay, so let's then use this, piece this together in natural logarithmic form. So we have, as soon as I put natural log, that base is already been taken care of. The base of the natural log is e. Then the exponent is the other side, right? Minus 4t equals minus 4t, because natural log and log functions generate or produce an exponent. There it is. Equals means generates that, produces that, and the result is x, like that. Okay? All right. So number 5, it says find the domain of each one of the following functions and write it using the interval notation. Aha. This is very interesting. Let's see what we have here that helps us answer this question. See, let me bring back the first page. What statement on here helps us find the domain of a log function? See, let me box this. The log of a negative number does not exist. Let me box it and say with an arrow, use to find the domain of a log or natural log function. That statement is going to help us answer these last two questions. Okay? The log of a negative number does not exist. It's as if I say the denominator of a fraction cannot be 0. Remember that? How many times did we use that understanding to find the domain of a rational expression? The fact that the denominator cannot be equal to 0, right? We would set the denominator equal to 0, solve for the value of x, find what that x value is, and then we would exclude it from the domain. So in this case, this understanding that the log of a negative number does not exist, we can use that to find the domain of a log function. Let's see how that's done. So that means that this 8 minus 2x is never allowed to be negative, right? Because log of a negative number, which would be 8 minus 2x, does not exist. So 8 minus, by the way, log of 0 also does not exist. I should have said that as well. So here, let me demonstrate. So if I take the log of 0, log of 0, error. So the log of 0 and negative numbers do not exist. Okay, so log of a negative number does not exist. Log of 0 does not exist. That affects how we find the domain. So 8 minus 2x must be greater than 0 at all times, right? This cannot be equal to 0, and it cannot be negative. Hence, 8 minus 2x must be greater than 0 in order for the log of that expression to exist. Okay, so let's solve for x using this inequality. So we have 8 greater than 2x, right? Just moving this to the other side and making it positive. And then dividing both sides by 2, which is a positive number, we get x less than 4, or x less than 4, just to put the variable on the left side. Okay? All right. So they're asking us to give this answer using the interval notation. So anything less than 4, right? So negative infinity comma 4 parenthesis. So the parenthesis indicates that 4 itself is not part of the solution. For anything less than 4 is the answer, is in the domain of that. All right? This is the domain. Domain of this function. This is guaranteed. Whenever you solve one of these on your own and you have questions about, you have doubts about whether your solution is correct or not, just one thing you can do immediately is just pick some test values, right? Put in 4. 4 times 2 is 8. 8 minus 8 is 0, and we cannot have log of 0 to base 5. We just can't. Okay, it'll be undefined. pick another value in this range that should work. So that would be 0, right? Plug in 0 here. What do you get? You get 8 minus 0. Log of 8 to base 5 certainly exists. So you can test it quickly. Okay, so now this one. This is not log, this is natural log, right? ln. So we know the base is e. Okay, but for finding the domain, we must guarantee that inside of this parentheses, or x minus x squared, is always greater than 0, or some positive number, some non-zero positive number. Okay, so for this inside here, we write x minus x squared must be greater than 0. Okay, so let's factor this out. This is a quadratic inequality. Remember quadratic inequalities? Remember what we did with those when we solved them several sections ago? X times 1 minus x greater than 0. So if you remember how we solved quadratic inequalities, it was first we would find the boundary solutions, right? Where are the boundary solutions? The boundary solutions are wherever the quadratic inequality is equal to 0. Okay? So then that would be, those are the boundary solutions. So from here we have x equals 0. From here we have 1 minus x equals 0. Therefore, x equals 1. So these are our boundary solutions. Wherever the quadratic inequality is equal to 0 is where the boundary solutions are. Okay, so let's draw the graph. I hope you remember what we did. So we have negative in the past when we talked about quadratic inequality solutions. Then, so this is positive, negative infinity to positive infinity, 0 in the middle. And we have 0, that's one of the, so we can't have 0 because the domain excludes 0. It should be left side should always be greater than 0. So I'm going to put a hollow circle there with a dashed line on top of it. And then 1 here, another hollow circle at 1, and a dashed line on top of it. So that would be 1. Okay? So we have, by now you should remember what we used to do for solving quadratic inequalities, right? So we checked each region to find where is the solution. So let's test the easiest number we can find in this region, which would be x equals negative 1, right? So testing x equals negative 1. So let's plug into this inequality. So we have negative 1 minus, that minus is this minus, and then another minus 1 squared. Okay, so I simply replaced, you could use this, I just picked that, I thought it was easier to use that, because this gives us the boundary solutions. That's what we're interested in. That's why we factored it. But when you pick test points, test x values, I think this is easier to work with. So minus 1 minus 1 squared. Okay, we're asking, is the left side greater than 0? Let's see. So that's minus 1. This is minus, that's positive 1. Minus 1 squared is positive 1. Minus 1 times that is minus 1. So minus 1 is minus 2. Minus 2 greater than 0. Is that true? Absolutely not, right? Minus 2 is not greater than 0. So in this region is not a solution of that. It's not in the domain of that natural log function. Okay, so let's test other x values. I'm going to put that here. testing an easy number here. Let's test testing x equals 0.5, right? Between 0 and 1. So let's plug it into this inequality. 0.5 minus 0.5 squared. We're asking if when we do that, is the left side greater than 0? That's the question we're investigating. So we have 0.5 here. The minus 0.5 squared is 0.25. We're still asking the question, and absolutely, right? This 0.5 minus 0.25 is 0.25, and that is greater than 0, definitely. So yes, between 0 and 1, it checks out. So yes. Now let's pick an easy number on the right side of 1. Let's pick 2. So testing, I should have left myself more room to solve this equation, or to answer this question, the domain question. So testing x equals 2, right? Let's substitute that into this inequality. What do we have? We have 2 minus 2 squared. We're asking if the left-hand side a positive number greater than 0 at all times, right? So 2 minus 4 greater than 0, that'll be minus 2 greater than 0, so that's false, right? So we end up with no. So the only solution region, or the only domain for this natural log function, is between 0 and 1, excluding 0 and 1. So domain is parentheses 0 comma 1 parentheses. Okay, I hope this is making sense. I thought that's a good example because it's mixing the domain of a log function, natural log function, with a concept we learned a while back, which was how to solve a quadratic inequality. When I ask you to review, all of mathematics is like this. Everything builds on the previous material, not necessarily in the same course, but in the courses you've taken before, Math 124, Math 96, when we had Math 96, and so on. So please don't skip reviewing the material. It's always helpful when you study a quantitative subject like mathematics. Okay, so we wrapped up this section. Thank you for persisting through this video, and I hope things are making sense. And until then, have a nice day. Until next time, have a nice day.